So in this video cast, we'll take a look at consequences of shapes and what it tells us about a molecule. So make sure you've got your notes out. It starts here with section 9.3 and we're going to go to the end, we hope. First, a quick review of shapes. Shapes, remember, are summarized by our shape chart. Make sure you've got this handy in your notes where we can say the bond angle, the name of the shape, the remember all, and then of course, most importantly, the bonded domains and the non-bonded domains. Should have those memorized. But what happens if we've got a big molecule? Say something like this. CH3COOH. This guy right here. And if we draw the Lewis electron dot structure for this critter, it ends up looking like this. And then we've got another C connected here with a double bonded oxygen up here. And then we've got connected to an O down here with an unshared pair of electrons to another H. Well, what's the shape of this molecule? Well, since it's a larger molecule, you actually have to break it down into its structures, and you could actually ask the question, what's the shape around this atom? What's the shape around this central so-called atom? And then lastly, what's the shape around this one? And you end up having different shapes for different portions of the molecule, and therefore different portions of the molecule can react differently, and they act differently. And if you look at this one, around this carbon we have 1, 2, 3, 4 shared, 0 unshared, and so we've got the shape tetrahedral. Around this portion right here, we've got 1, 2, 3 bonded domains, or 3 shared pairs of electrons, 0 unshared pairs, and so the shape name for that one for 3 shared and 0 unshared pairs is trigonal planar. Trigonal planar, because we're all in the same plane. And then right around here we've got 2 shared and 2 unshared pairs right here, and so this gives rise to the shape called bent because there's 2 unshared and 2 shared pairs. So when you're confronted with a larger molecule, but make sure that you look at the various shapes of the various sections. So what does this tell us about a molecule? The first and most important thing it tells us about a molecule is something called its polarity. And we learned back in chapter 8, that if we have 2 atoms, for example, a carbon and an oxygen, I'll just draw a carbon dioxide molecule down here, and the oxygen atom in this case is more electronegative than the carbon atom, that we can build up what's called a bond polarity or a bond dipole moment. And this double bond right here is called a polar bond, where there's a partial negative charge and a partial positive charge building up right here. This polar bond causes there to be more density of electrons and a more negative charge built up on this side of the molecule. Now, the same thing happens over here in this part of the molecule, where there's a pull for electrons towards this oxygen, and there's a partial negative charge here, and once again there's a partial positive charge that builds up over here. Now, besides bond polarity, there's also overall molecular polarity. And what we want to answer with that one is, hey, where in this molecule is there a more dense area of electrons? Your book does a really nice job of showing a picture of this. Here's the carbon dioxide molecule, and you can see that they show a partial negative charge out on each oxygen and a partial positive charge over here. Maybe I just need to bring it closer. That'll probably look a lot better. Let me back this off a second. So here you can see the carbon and oxygen partial overall dipole moment pull this way and pull this direction. And since they equal each other out, we say that the overall dipole moment of the entire molecule is actually 0. And you can see if you show an electron density right here, that there's a pull in this direction for electrons and a pull in this direction for electrons, and they actually even each other out. And therefore, in terms of what's called bond polarity, there is a polar bond here and a polar bond here, but in terms of overall molecular polarity, there is a dipole moment of 0. And the molecule itself is said to be nonpolar, a nonpolar molecule. In other words, it has no place in the molecule where there's a buildup of negative charge. Now, I know that the bonds themselves are polar, but the molecule is nonpolar. And this becomes fairly significant, well, extremely significant, because then it decides whether or not molecules will stick to other molecules. Because if they, of course, have a partial negative charge here and another molecule has a partial positive charge, they'll attract each other. But in this case, since there's no overall area, the carbon dioxides have a tough time sticking to other carbon dioxides. Let's take a look at a second example. Let's look at water, H2O. If you draw its Lewis dot structure, it ends up looking like this, where we have 2 unshared pairs of electrons and 2 shared pairs of electrons, which gives rise to the shape called bent. And if you remember, this bond angle right here for a bent structure ends up being 104.5 degrees, which is a little bit less than what the tetrahedral 109.5 degrees is. This causes the polar bond right here between oxygen and hydrogen, which would cause a buildup of a negative charge up here by the oxygen, to be significantly strong, and a buildup of positive charge down here by the hydrogen, because of the exposed hydrogen nucleus, to be quite strong as well. Which means that this part of the molecule up here, where these unshared pairs of electrons are, that are negative in and amongst themselves to start with, to be very negative. And this part of the molecule down here, where the exposed hydrogen nuclei, to be quite positive. This makes the overall molecule to have a significant dipole moment in this direction. A significant dipole moment in this direction. And therefore we say that this molecule is polar. This molecule is polar. There's a negative charge here and a positive charge down here on the bottom of the water molecule. Your book does a nice job of illustrating this. I'll hold it up a little bit closer here. You can see that here's water molecule pulling for electrons this way, pulling for electrons this way, and there's a negative charge building up on the oxygen atom and more of a positive charge down here on the hydrogens. And you can see from its electron density map here we've got a lack of electrons, and therefore a positive charge, and here we've got a buildup of electrons, and therefore it's very negative here and very positive down here in this part of the molecule. That is super duper important. Determining whether a molecule is polar or not depends on 2 things. Depends on 2 things, and we're going to write those 2 things down. Number 1, got to have polar bonds. If it doesn't have polar bonds, it can't be polar. Okay? And then number 2, it depends whether the molecule is symmetrical or not. Symmetrical is kind of a fancy word, but I think most of you know what it means. Symmetry means that it matches itself. So for example, in the carbon dioxide molecule, if you cut it in half, the halves would match. If I cut it in half, the halves would match. Here, if I cut the water molecule in half this direction right here, the halves down here and this half up here would not match. And since it's asymmetrical, it is nonpolar. Nonpolar. Now, polar bonds aren't always totally necessary for it to be a polar molecule. I'll give you one strange example a little bit later in the video cast. But symmetry is the #1 cause of making a molecule polar or not. And being able to determine whether there's dipole moment throughout the molecule is critical to its intermolecular forces and the way that the molecule acts. Here's a picture in your text of some different polar and nonpolar molecules. You can see right here, here's an HCl molecule, and it's very polar, pulling this way, negative charge, positive charge here. The overall dipole moment would cause it to be polar. Here's CCl4. You can see it's a tetrahedral shape, and so it has pull for electrons towards each one of the chlorines, but they even each other out. And so overall, even though it has polar bonds, this is a nonpolar molecule. This guy right here has an unshared pair of electrons on the nitrogen, and since it's an uneven distribution of electrons causing 107 degree bond angle right here, this squishes these together, causing a partial negative charge here, a partial negative charge here, and a partial positive charge down here where the hydrogens are. So that's a polar molecule. This guy right here, nonpolar, because it has a trigonal planar shape, even though it has polar bonds, nonpolar molecule. And this guy right here would be polar because there'd be an uneven pull for electrons right here towards the chlorine and more positively charged here around the hydrogens. So those are some examples of polar bonds polar molecules, and you too should become good at determining from the shape whether a molecule is polar and has a dipole moment or not. Going on, section 9.4, covalent bonding and orbital overlap. Well, the VSEPR model, VSEPER, that's the one that gives us the shapes, provides a simple means for predicting the shapes of molecules. However, it does not explain why bonds exist between atoms. In developing theories of covalent bonding, chemists have approached the problem from another direction. They used a thing called quantum mechanics. Well, how can we explain the bonding and account for the geometries in molecules using atomic orbitals? Remember, atomic orbitals are like the S, sphere, P, these, dumbbell-shaped things, and the Ds that look like flower petals, and etc. How can those things actually show that the orbits share electrons and therefore overlap? Well, here's one of the approaches. Let's say it's two s orbitals in hydrogen atoms. These two would overlap this way, and we'd have an orbital overlap right here, and this area where they overlap would be the shared region of the electrons. Let's say it's an s and a p orbital. Notice here now we have an orbital overlap region, and we'd have the sharing going on here. Let's say it's two p orbitals. Now we'd have them overlap here, and we'd have this area being the sharing of those electrons. So we can see from s and p orbitals, the way that we talked about them in quantum mechanics, we can have that overlap and have that area where we have electrons overlap with one another. Now, this doesn't always work. And so scientists have said, okay, this s and this p orbital don't overlap all the time perfectly. And so let's take a look at s and p orbitals, and if I draw these in terms of orbital notations, s's can hold a total of 2 electrons. P's, remember, have 3 orbitals, which can hold a total of 6 electrons. Remember, each arrow illustrates an electron. And so we have 1 s orbital and 3 different p orbitals that in essence could eventually overlap and cause bonding to occur. Now, although this overlap of s and p electrons allows the understanding of the formation of covalent bonds, it's not always easy to extend these ideas to molecules that have more than just one bond. And so scientists have said that these s and these p orbitals sometimes combo. I shouldn't say sometimes. They almost always do. And when they combine together, we give them a fancy name. We call them hybrid orbitals. And so we take an s orbital and a p orbital. I'm going to do my best in drawing this p orbital. Remember, it looks kind of like a dumbbell right here. And we shove them together. And when we do that, we get an orbital that looks something like this, and then an orbital that looks something like this. And these two orbitals combo together to form like a giant P orbital that looks kind of like that. Now, your book has a much better picture, and it shows them right here. Here's the s orbital. Here's the p. Those combo together form this thing. And then it really looks like a large hybrid p orbital. These combo hybrid orbitals, since it's a combination of one of the s's and one of the p's, is called an sp hybrid orbital. Now, this allows us to overlap something and cause 2 bonds to occur. For example, in your textbook, it shows how a beryllium atom right here would form bonds with 2 fluorine atoms. And if you don't have your textbook out, you might want to take it out and open to this page. Pause now to do that. And then you can see these pictures a little bit better. But you can see that this fluorine orbital would then have 2 hybrid sp orbitals to overlap with in beryllium and form these bonds and have this overlapped area where the electrons are actually shared. This would be called an sp hybridization of the beryllium s and p orbitals. Well, what happens if there's more than 2 bonds? Like, for example, in something that looks like this, B, and then it has maybe like 3 fluorines attached to it, something like that. Well, now this boron has to have 3 areas where it has an orbital, an orbital, and an orbital to overlap with the fluorine. If you look at boron's electron configuration, it's 1s2, 2s2, p1. 2 electrons here, 1 electron here, and since these 2 electrons are stuck together in an orbital, there must be a way to get them separated, so then we can have 3 areas to have bonding overlap with the fluorine atoms. They hybridize. And we end up with the s orbital comboing with the p orbitals right here, and we end up with the s and 2 p's comboing together to form the sp2 hybridized orbitals. Your book does a better job of showing this. Here's an s, here's 2 p's, combo them together, and we get 1, 2, 3 orbitals in a trigonal planar geometry that allows 1, 2, 3 areas of bonding to occur. Okay, in terms of Lewis electron, in terms of orbital notation, we take the 2 from the s's and the 2 from the p's right here, combo those together, and we can make 1, 2, 3, 4 orbitals right here. And so when we have something with 4 bonded domains, that was my next step, to go on and do something like CH4 right here, we can take the 2 S2s, 2 of those, and the 2 P2s, and we can combo 4 of those together to make 4 hybrid orbitals, and these are called the sp3 hybrid orbitals. And you can see your book has a better illustration of that. I just showed you a second ago the orbital notation of that, but here's the actual physical characteristics. A spherical, P, P, and P, combo them all together, and we get 1, 2, 3, 4 hybrid orbitals, each one at the edge of a tetrahedron, giving us the 109.5 degree bond angle. CH4 would be an example that has sp3 hybridization. Well, what happens if we have more than 4 bonds forming, like for instance in something with a trigonal bipyramidal or a octahedral electron domain geometry? Your book does a nice job of dealing with these as well. Okay, here's a summary chart of geometric arrangements characteristic of hybrid orbital sets. Here's the sp hybrid orbitals, sp2 hybrid orbitals, sp3 hybrid orbitals given the tetrahedral, and this is the sp3d. Since we ran out of p orbitals, now we have to go in and grab a d, and so it's called sppd hybrid orbitals, giving us the trigonal bipyramidal organization. And then lastly, sp3d2, we can add 2 d orbitals there to give us the octahedral electron domain geometry. And they've got a number of examples of Lewis electron dot structures that actually fit that and then allow us to have that hybridization. So by now you're overwhelmed with this hybrid stuff and you're like, what the heck does this mean? Can you just give me a couple examples and show me how to figure it out easily? And I can. I got to turn this paper over really quickly. And let's just look at a couple of examples and figure out what the hybridization is about these particular substances. Let's take a look at something like PF5. And let's ask these questions. First of all, draw the Lewis electron dot structure. And then from that, will you find the shape name for me, please? Shape name. And then once you found the shape name, will you find the bond angles for me, please? And then from there, will you tell me the hybridization about the central atom, and whether it's sp, sp1, sp2, sp3, sp3d, sp3d2. Summarizing the hybridizations, once again, there's sp, which involves an s and a p orbital, gives head-to-head orbital overlaps for 2 bonds, sp2s, sp3s, sp3d, and then sp3d2. Those are the 5 possible hybridizations that occur. Okay, so let's take a look at PF5. First of all, add up the electrons. Phosphorus has 5, fluorine has 7, times 5 is 35, plus 5 more means we have 40. So if we draw the Lewis electron dot structure, we're going to get a phosphorus with 5 fluorines around it. And phosphorus can do that because phosphorus can have more than an octet, because phosphorus, remember, is in the 3rd period, and anything 3rd period or below, remember, can have an expanded octet. And then let's bond the electrons around the fluorines. And that gives us 8 around each fluorine, and 8 times 5 is 40, so that uses up all of our electrons. So here's the Lewis electron dot structure for it. Now we need the shape name. Well, we have 1, 2, 3, 4, 5 bonded, 0 non-bonded. And if I look back on my shape chart, in case I don't have it memorized yet, 5 bonded, 0 non-bonded, 120 and 90 degree bond angle, called trigonal bipyramidal. Trigonal bipyramidal, okay? Trigonal bipyramidal, and the angles are 90 degrees and 120 degrees. Hybridization here now. Here's the easy way to find the hybridization. Look at each one of the bonded or non-bonded domains around the central atom. Take your right hand, make a fist. S, P, 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 D. That's my 5 domains. And each one of my fingers stands, my thumb stands for S, my next 3 stand for P's, this one stands for a D, and if you end up needing another D, you got to grab another finger. But S, P, 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 D, it happens to be sp3d hybridized, because we've got 5 electron domains around the central atom. Shared or unshared, doesn't matter, they're still hybridized. And that's my hybridization around the central atom. Let's look at a second example. One more. How about kind of a fancy one here. How about this thing? BRF3. BRF3. Okay, let's draw the Lewis electron dot structure. 7 plus 7 times 3, that's 21, plus 3 plus 7, that's 28. Put the least electronegative atom in the center. Bond the fluorines around it. 2, 4, 6, 8, 10, 12, 14, 16, 18. 3 times 8 is 24. So that means we've got 4 electrons left over. Well, bromine can break the octet rule because it's in the 3rd period or below, so let's put 2 unshared pairs on that bromine, and then we for sure complete the octet. And it ends up here having 1, 2, 3 bonded domains, 2 non-bonded domains, and when you've got something like that, I believe you have a shape called T-shaped. T-shaped because we got 3 bonded, 2 non-bonded, 90 degree bond angle right here. And then if you want to know the hybridization, look at all of the bonded and non-bonded electron domains. Take your fist, put it out in front of you. S, P, notice I count the non-bonded, P, P, D. Oh, so it's sp3d hybridized. Even though not all of them are bonded domains, you still count the non-bonded guys right there, and it's sp3d hybridized. All right, so there's some good examples of using hybridization, and then you can figure out how the S and the P's come together to make a bonded and non-bonded domains. So you can figure out what the hybridization of those substances are. Last thing, multiple bonds. Multiple bonds, very last thing. But when we have more than one bond, like for instance a carbon-carbon double bond, and then we've got maybe some hydrogens attached right here, these double bonds are actually composed of 2 different things. 2 different things. One of these bonds right here is a head-to-head orbital overlap. A head-to-head orbital overlap of an sp2 hybridized orbital. Because we've got 1, 2, 3 hybridizations going on right here. Because this would be sp2 hybridized about this carbon atom. This one also sp2 hybridized, because you count a double bond as only 1 electron domain. And then we've got this extra bond in here that makes it be a double bond. And this extra bond must be a little bit different because it's not a head-to-head orbital overlap like the sp2s would be. And as a matter of fact, it's a p orbital. This is a p orbital that leans over and attracts to the other p orbital of the carbon right here. And your book does a tremendous job of showing this. Tremendous job of showing this. Right here, in this picture, you can see that we've got a hydrogen and a carbon, hydrogen and a carbon, hydrogen and a carbon, hydrogen and a carbon. And right here, we've got the head-to-head internuclear axis overlap of the carbons. And then we've got these p orbitals right here that will actually overlap and attract between the p orbitals right here. And this forms a special type of bond between these p orbitals and the carbon. This special overlap is known as a pi bond. Okay, so we have two different types of bonds. In a double bond, in a single bond, and in one part of a double bond, we have a special bond that's called a sigma bond. It's not special, it's just sigma. It stands for single bond, or the single part of a double bond. This sigma bond is characterized by a head-to-head orbital overlap between the hybridized electrons. The second part of the double bond right here is an extra bond, and this extra bond is known as a pi bond, like the Greek letter pi. And the sigma bond is actually the Greek letter sigma, which looks like this. And the pi bond is not as strong as the single bond, because it's p orbitals that are actually like overlapping on the top and the bottom, and the overlap on the top and the bottom are not two separate pi bonds, it's one pi bond, okay? This overlap right here, and it's not on the internuclear axis, it's above and below, that causes these to kind of lean over and attract to one another. These pi bonds aren't as strong. This explains something that I foreshadowed for you way back in chapter 8 when we talked about bond strength. And when we talked about bond strength way back in chapter 8, we actually looked at something called bond enthalpy. And in this bond enthalpy, we said, oh, take a look at single bond strength versus double bond strength versus triple bond strength. And I'm just going to go back in the notes here just a second. I'm going to go back here in the notes just a second to chapter 8 at the very, very end, where we looked at this table in your textbook. And this table was table 8.4, and we talked about covalent bond strengths. And I pointed out to you here, this carbon-carbon single bond, carbon-carbon single bond right up here, was 348 kilojoules per mole. Then this carbon-carbon double bond was 614, carbon-carbon triple bond was 839. I'm going to write those down really quick, and you should write these down too. I'm just going to go on this side of the paper so I can draw it nice and big. A carbon-carbon single bond has a bond enthalpy of approximately 348. This is in kilojoules per mole now. Carbon-carbon double bond has a bond enthalpy of approximately 614, and a carbon-carbon triple bond has a bond enthalpy of approximately 839 kilojoules per mole. Why, since I have a double bond here, is it not twice as much as this 348? This 348 is pretty close to 350. This should be about 700. And if this is 350, this should be triple the amount, and it should be like on the order of 1,000. But it's not. The reason for this is the type of bond that we have here. Now remember, in a double or a triple bond, only one of the bonds is what's called a sigma bond, where there's a head-to-head orbital overlap of a hybridized orbital. This has a bond enthalpy of about 348. These extra bond or bonds in the double bond here, one of them, or two of them here, are what's called pi bonds. And the pi bonds, remember, aren't as strong because they don't have that head-to-head orbital overlap. They've actually got a leaning bond towards them of the pi bonds. Let's take a look at this example again right here. You can see in this picture of your textbook, here's the sigma bonds between the carbon and the hydrogens, and then these pi orbitals that are not hybridized lean towards each other and form this pi bond right here above and below the internuclear axis. These lobes of the one pi bond right here make it so it's not as strong as the internuclear axis sigma bond. Here's another example right here. In the C2H2 molecule, you can see here that there's a sigma bond right here, a single sigma bond here, and a single sigma bond here. So about this carbon atom, it'd be sp hybridized. Sp because there's only one s and one p orbital involved in single head-to-head overlap bonding. And then you can see here in these p orbitals, there's a pi bond that occurs, and the above and below is one pi bond, and then there's one that occurs on the side here and one that occurs on the side here. And so you can see in this triple bond we have a sigma, a pi, which is illustrated by the top and the bottom, and a pi, which is illustrated on the side and the side right here. That is what makes triple bonds not as strong as just 3 times a single bond. So you should be good at determining whether something has a single, double, or triple bond, and therefore whether it has sigma and pi bonding. Your book goes on to show how multiple bonds in the structure called benzene, C6H6, actually forms these resonance delocalized pi bonds around the center of it. You can see right here, here's the CH's, and then you've got the head-to-head orbital overlap all around. But then they've got these unhybridized p orbitals that actually lean over and form this ring of pi bonds above and below, which cause it to have these delocalized pi bonds, and that's why we have that thing called resonance from back in chapter 8. This occurs in a bunch of different structures, and your ability to determine whether something is sigma or pi bonded lots of times gives you a clue as to the strength and the ability of things to stick together. Good luck with your sigma pi bonds, hybridization, and polarity in structures.